we see at the top of the table, we have our goal, right? So the goal, when we want to compare mean scores between two independent groups, such as the example, does the mean level of class attendance differ by class assignment in the morning or evening? We would use the parametric procedure, independent samples t-test. And we would use the non-parametric procedure, the Mann-Whitney-U. All right, so we won't go through these each at a time. We'll go through each one and then apply it. All right, so that's what we'll do right now. All right, the Mann-Whitney-U. So if we go to our SPSS instructions, this is what it looks like. But let's go to the actual SPSS. Now observe, we're looking at class assignment, right? Morning or evening by class attendance. So here's the instructions, but here's the actual doing. So analyze, and we go all the way down to non-parametric tests, legacy dialogues. So there's a couple of ways to do it. This is one of them, right? Two independent samples. No big deal, all right? May elongate it. So we find class attendance, put it in the test variable. Now the grouping variable, that's our categorical variable. And first we're going to look at class assignment. Now it's coded as 1 and 2. Put the 1 and the 2. And then click either paste, right, save it in the syntax, which is always a great idea, or OK, right? And you'll see here under type, the Mann-Whitney-U is checked by default, right? So it's going to be checked when you open it, at least in this version of SPSS, but there it is, checked and OK, right? So there is the output. So let's look at the output. Here we go. So the Mann-Whitney-U test results, right? So here we go. What do we look at? Right here, right? So that bottom box, at the last line in the bottom box, that says ASYMP sig two-tailed. That's the statistical significance. So the non-parametric Mann-Whitney-U test indicates there's a statistically significant difference in mean attendance, right? Class attendance, mean levels of class attendance for the morning and the evening, right? And we know the evening is higher from our descriptives. So we also need to look at, right, class instructor, because that's our other dichotomous predictor that we have in our mixed method study, right? So that's the category, you know, class instructor is either Miss Gettenline or Miss Albright, right? And then if we look at the bottom, in our second Mann-Whitney-U test, we see there's also a statistically significant difference between levels of mean attendance, mean class attendance, you know, by class instructor. And we know Miss Albright has a significantly higher level of attendance in her classes. So those are our first non-parametric tests. And you can see they're quite like the independent samples t-test, right? You have your significance, and you know which mean is higher. Now next, what if we would like to apply a non-parametric test where we have a categorical variable with 3 or more categories and a continuous variable, right? So for example, right, if we wanted to look at mean levels of class attendance, right, by doctor prescription status, which is no, recommended, and yes, right? For the parametric test, it would be a one-way ANOVA. However, for the non-parametric test, we would use the Kruskal-Wallis test. Okay, so let's look at that in SPSS. Okay, so analyze. Again with the non-parametrics, right? Again, non-parametric test, legacy dialogues. Okay? And then non-parametric test legacy dialogues, keep zipping away there, then K independent samples. And you'll notice here the Kruskal-Wallis test is also checked by default. So we don't have to check it, but we want to make sure it is checked. So then we take class attendance and we put it in the test variable. Right? It's kind of just like the one-way ANOVA, and doctor prescription status, and we put it in here. Now the range, you have to define the range. So 0 to 2, right? Because 0 is no, not prescribed, and then there's 1 and 2. And continue, and then either paste or OK. Say OK, there we go. There's the results. We'll look at them on the slide. Right, so there's the instructions we just went through. There's the results, and what do we look at? There you go. So we see the significance, right? There's not a statistically significant relationship between doctor prescription of classes and class attendance. Now we know that there actually is that relationship among the whole 100, but using our test here, it's not detected, right? So if we only had our 25 to look at, we wouldn't know there was actually a relationship, right? So that's what that indicates. Now, lastly, suppose we wanted to estimate the degree of association between two continuous variables, right? For example, suppose we wanted to see if class attendance, right, increased at a significant level as class enjoyment did, or the other way around too. So if class enjoyment increases, does class attendance go up? We would use the Pearson-R correlation for parametric tests, but the non-parametric equivalent would be the Spearman's rho. So these are the results for the Spearman-Rho correlation. The actual Spearman-Rho is the exact same, I'll show you, the exact same as a correlation we did earlier. You just modify it a little by your checking. So recall, we go to analyzing correlation just like in week 2, then bivariate just in week 2. The trick is the Pearson correlation is checked by default. So you want to, well, you uncheck it and then check the Spearman's rho. And then you just put in your variables like before, class attendance, age, and class enjoyment, right? Then either paste or OK, right? And there's our findings. Right, so it's just a little slight modification of the original correlation we did. Anyway, there's what we look at, right? The statistical significance. That's what we want to see at the bivariate level, which is what these are. These are the non-parametric tests are the equivalent of bivariate tests. So neither are related. Now we know with the larger sample of 100, class enjoyment is related, but you could see that relationship is not being detected among the 25 residents like it was evident among the 100. So here are the results of our non-parametric tests, right? The ones we just looked at. So we see that the covariate variables 1 through 3, age, doctor prescribed, classes, and class enjoyment are not significantly related to the dependent variable class attendance, measured as 0 to 7 days weekly class attendance. However, we do see that the two last variables, right, our two categorical predictors, are significantly related to class attendance, that being class assignment, mornings or evenings, or class instructor, Ms. Gettenline, Ms. Albright, right? So we did detect those big relationships like we did with the full 100 residents in our analysis. All right, so as we said, non-parametric testing here is the equivalent of the bivariate tests in parametric testing, right? So we could see, right, what's significantly related, which variables one-on-one are significantly related to class attendance, right? So we could see those significant one-on-one relationships just like we did in week 2 with the t-test, the ANOVA, and the correlation. right? The Pearson-R correlation. But, right, we can't see which is the strongest predictor, right? Now recall, that's our research question. What's the strongest predictor of class attendance? We can't see that. There's no multivariate test, as we said, where we could put both independent variables in a regression model and see which is the stronger predictor of the dependent variable class attendance, right? So this is the limitations of non-parametric tests. We can't answer the research question and a hypothesis. Right, so we can't see the strongest predictor. Now for us, knowing what we know from our full analysis with the 100 residents, that's a really big problem, because we know in the regression model, the multiple linear regression model, that when both independent variables were entered, right, class instructor canceled out class assignment, right? So we know that once you consider who's instructing the class assignment no longer matters anymore. But if we just did non-parametric testing, we can't get that take-home message, right? So that underlying message is missed if we only go to the bivariate level. So this is where we say combining the parametric and non-parametric tests to examine the data provided by the 25 residents, right, is our way of assessing the data as thoroughly as possible. Okay, so we'll carefully incorporate, these analyses. We'll list the limitations, the strengths, the reasons for using both, right? So the first thing we should do, right, so if we're saying the non-parametric complements the parametric, we should repeat the parametric test with this smaller sample of 25. We should see if we get the same findings with it as the parametric, and typically you do. I've rarely seen where they weren't the same findings, which is good because they corroborate, the relationships between variables, which is what we're looking for. So let's first consider, our one-way ANOVA. Is there a significant difference, like in mean scores for class attendance, by the doctor prescribing class? Okay, so now we're doing the parametric versions of the non-parametric tests we just did. Now remember, we have all these test assumptions for the one-way ANOVA, right? And with only 25 residents, some of them might be violated. You should go through and examine each one so you could list which are met, which are violated. But also pay attention to the bottom there in terms of statistical power, right? So this is just statistical power overall. In the bottom, you'll see, right, if you have seven cases per cell, so if you have 7 cases per cell within those 3 categories, right? So you have 3 categories: prescribed no, prescribed recommended, prescribed yes. If you have 7 within each, which is about 21, that's about our full sample, you only have 50% power to detect a large effect. Now we'll discuss that in a minute, but keep that in mind. So here are the results of the ANOVA. Again, this was presented in week 2, so we won't go back and go through. Now look, the model is not statistically significant, so we don't have to worry about the rest of the findings, right? So the parametric test corroborates the non-parametric that doctor prescription is not associated with class attendance when only using the small sample of 25 residents. Now pay attention, right? So if you look at the means, the mean level of attendance for those who were recommended, class, right? That's only 6 people, right? So there's 13 no's, 6 recommended and 6 yes. So that's very low statistical power, right? Because there's actually less than 7 people in each cell, right? So that affects the statistical power. But you can see the mean for yes is high, it's 4. And for the other recommended and no, they're below 3. So it's a more than a day-a-week difference, but it doesn't achieve statistical significance because we don't have enough people in each cell to get statistical power to indicate that relationship, right? That's one of the limitations, right, of our small sample research. But that, like I said, that's a limitation of small sample research, so it's intrinsic in the process. So again, our t-test, we're looking at if mean levels of class assignment, mean levels of class attendance differ by class assignment. Again, we have our assumptions. Check them out, right? But then also notice you need 30 participants per cell, to detect a medium-large effect, right, with 80% power. We can't have that because our whole sample is only 25. So it's more like 15 people per cell we'd have. Right, so there are the results of the t-test. What do we look at? Right, the center column in the bottom box, the p-value is below 0.05, so a statistically significant difference, right? And the evening classes have the significantly higher mean attendance rate at 4.59 relative to the morning classes of 1.75, right? And you'll notice there's 14 people in the group in the morning and 11 in the evening. So these means, right, even though it's fewer people, do reflect the larger sample of 100. Right? And then we also want to look by class instructor. And there's our t-test. And again, the bottom box center column indicates a statistically significant finding below 0.05. And then when we look at the top at the mean level of attendance for Miss Albright's class is almost 5 days per week, right, 4.9. And the mean level of attendance for Miss Gettenline's is 1.25. So just a little over 1 day per week. So it's a major difference. And then finally, we have our Pearson R correlation. So this is the parametric equivalent of the Spearman-Rowe correlation we just did a few minutes ago. So again, we have our test assumptions. And then we have our correlations, right? Pearson R correlations, so the parametric version. And then we see also there's not a statistically significant relationship, right, between the predictors and the dependent variable class attendance. So if you look at the parametric versions, right, so the bivariate test, which are the equivalents of the non-parametric test, right? So both of them are bivariate testing level. The findings agree, right? So what that's saying is that even though the assumptions might not be met, the tests appear to be robust, because when the assumptions are not considered in the non-parametric tests, the same relationships are produced as in the parametric tests, right? So in other words, the two significant predictors of class attendance are class assignment and class instructor. Right, so now here's where it'll get interesting, right? So we have our complements, we have our bivariate findings, right? We know that the findings corroborate one another, okay? That's our big considerations. Now, also keep in mind either the significant covariate dependent variable relationships that we know exist within the full sample, right? Specifically, class enjoyment and doctor prescription status, right, was not related to class attendance. Why? Well, first, right, the first little dash, low statistical power. Even if there was a big effect, we really didn't have enough statistical power to detect that relationship. And then the second dash, of course, if there was a small to medium size effect, obviously, if we didn't have enough for the big effect, if there was smaller effects, we're less likely to detect them, right? And also, the 75 people left out, right? So we have 25 people in the sample. The 75 people left out may have been driving those findings, right? Okay, so note the significant bivariate relationships, right, that were detected, right, we know have big effect sizes, right, between the independent and dependent variables. Otherwise, we may not even have seen those, right? So we got the big dramatic ones that we did pick up on. That's right, and then the other ones not so much. So now we're going to go beyond where we left off with just the parametric testing. Okay, so we're going to use multivariate analysis, the multiple linear regression, to test the relative strengths of the independent variables. Okay, so we're going to go beyond the bivariates. We're going to find the strongest predictors, right? And since the only two significant ones were class assignment and class instructor, at the bivariate level, those will be the only two in the linear regression model. So we do our linear regression, just like week 2, and these are our results. Now pay attention, right? So we actually do get the same results as we did here with the first 100, where the strongest predictor is class instructor, and it has a very big effect size. The PES, partial eta squared, is 0.66. And also notice the same thing happened where when we put class instructor in the model, class assignment was no longer statistically significant, meaning when you consider class instructor, class assignment to the evenings or mornings no longer matters in explaining class attendance. Also noteworthy is, notice that the R squared is 0.82. So the R squared is how much variance in the dependent variable is explained by the predictors, right? So it's unlikely that these two predictors explain 82% of the variance in class attendance, meaning that these two predictors explain almost the entire reasons why people do and don't attend class 0 through 7 days per week. Right? So that's not realistic, but even though this is probably not the actual effect size in the population, this high effect size suggests, right, that there's a really strong relationship between the class instructor and attendance. Right? So our results, right? So the bivariate level, we saw class assignment, class instructor were significant predictors of the dependent variable. At the multivariate level, we see instructor as the strongest predictor, and it cancels out class assignment, as we said. We failed to detect some of the significant relationships between the covariates of the dependent variable that we know exist, right? Even so, the research question and hypothesis was answered in the same manner with these 25 residents as it was with the full sample of 100. Now, as I said, typically researchers can't compare if they actually got the correct representative findings relative to the whole population per se. So this is just, for the sake of learning, and it's a little benefit for us. Right? Normally, we don't know, right? We have our findings. Do they represent the whole population or even the whole community? We're not sure usually. But for us, we know they did. So when we're publishing this, right, as a manuscript or in a research report, how would we describe what we did, right? So the shorthand is, you might say something to this effect here, right? So due to the relatively small sample size, right, certain assumptions of the parametric tests were not met. And we might list, like we saw class enjoyment. Class enjoyment did not have a normal distribution. We would look at each of the assumptions and say which ones were and weren't met, right? So then we say, therefore, non-parametric tests were used, right, to examine the bivariate relationships, right, between the predictors and the dependent variables. Non-parametric analysis indicated like findings in terms of, the same statistically significant relationships. Therefore, it seems that the parametric tests were robust, right? So that's a tremendous use of the non-parametric tests, right? So we're saying even when the assumptions weren't present, we got the same findings as when the assumptions were present in the parametrics, but maybe slightly violated. Now, recall our qualitative analysis. Remember, when we said we need to reach saturation and redundancy, right? When we're doing data collection, saturation and redundancy is the point where the same themes and sub-themes are emerging in the data, right? So we were wondering, we said probably you're reaching saturation and redundancy way far below 100 people, as in you're going to see the same themes and sub-themes with a small number of people that you will with 100 people, right? And that's qualitative data is based on that, right? So what we could do is compute the percentages of residents that indicated the same themes and sub-themes for the 25, sample of 25, and compare them with the sample of 100. If the percentages are similar, right, it may suggest we did reach that saturation and redundancy way back before we had a full 100. So if we do that, now look at here. So you can see the themes, right? So for theme 1, so you can see they match actually pretty well, right? So for theme 1, right, for the full sample, 90 people, which is 90%, mentioned things that would encourage attendance. For the 25, it was 23 people, which was 92%, right, of residents that mentioned things to encourage attendance, right? So it's pretty close. And then the respective 3 sub-themes for the sample of 25 is 72%, 76%, and 60%, relative to the same 3 sub-themes for the full 100, 77%, 85%, and 55%. So they match pretty well. So it does suggest that saturation and redundancy was seen earlier, and also for the barriers. For the small sample, 19 people, which was 76%, mentioned some kind of barrier. And for the full sample, it was 65%, so about 10% difference. That saw some barriers. Then if you look at the 4 sub-themes for barriers, it's 16%, 28%, 20%, and 16%. And that matches pretty well with the full sample of 100, right, which is 15%, 25%, 19%, and 10%. So it does suggest, right, that we saw saturation and redundancy early on, as the same percentage of residents indicated the themes and sub-themes pretty closely relative to the small sample and the full sample. In other words, to put it in plain English, right, we see in the small sample that a large percentage, the largest percentages of sub-themes were people saying they prefer Mrs. Albright, sub-theme 1 in theme 1, and morning attendant, sub-theme 2 in theme 1. And the same pattern is evident in the full sample and the small sample. So we would have known with the small sample that people want to go to Miss Albright's class and people want to exercise in the morning, and that's the biggest theme that was evident. Right, so other options for small samples research. Now, recall we also look at the dependent variable as a dichotomous variable. You know, did the resident attend class 3 days a week or more? Now, yes, no, right? Now, that primarily involved, if you recall that analysis, chi-squares and binary logistic regression. Now, so we were looking at non-parametric tests. The chi-square is a non-parametric test with few assumptions. The binary logistic regression has way fewer assumptions than multiple linear regression, so it often accommodates a smaller sample better. Right, so if we were doing that analysis, right, that's the easier one to do with the small sample, so that we did the harder one. But if you're doing an analysis with a dichotomous variable, it's much more straightforward many times with the small sample. You don't need many parametric substitutions because the bivariate test, the chi-square, is already non-parametric, right? So you'd use the same thing with the small or large sample. Like I said, binary logistic, it doesn't have assumptions like a normal distribution, so if that's violated, that's not that much of an issue, right? So in other words, to sum it up, when you have a small sample or a large sample with a dichotomous variable, the analysis it matches pretty well. It's almost the same analysis. It involves chi-squares and binary logistic regression. So that's another thing to consider. So if you have a small sample and you're doing an analysis and there's a reason to dichotomize a continuous dependent variable, like we had a cutoff score of 3 days or more, right? If there's a reason, like, you never want to do it arbitrarily, like just dichotomize a dependent variable arbitrarily, but if there's a reason to do it, you might want to consider that and use a dichotomous dependent variable with small samples research. So, in conclusion, to sum it all up, non-parametric analysis was used to address the challenges posed by research involving a small sample. Non-parametric tests have a useful but limited application. We saw that. Now, our study, the non-parametric analysis, was effective in answering the research question and hypothesis, right? We had a combination with parametrics, right? So what that was meant to illustrate is an effective analysis is possible even when you have a small sample size. All right. Next week is our final week. We will be looking at the write-up and report of these findings, right? So that's going to be interesting because normally just writing and reporting one of them is a process. So we have a process and a process. All righty. Well, thank you for watching, and I will speak to you soon.